Hello again, students. It's Professor Bell, and I wanted to dive into a few things still within that first chapter or two. Some of these graphics that you're going to see are from chapter 2, but I'm not going to cover everything piece by piece, so some of it will get left out. But what I want to look at is Earth-Sun relationships, maps, representations of Earth, certainly latitude and longitude. And so I just want to touch on a few of these things. So to start off with, looking at the planet, Eratosthenes, I can never say dude's name, is the first geographer. He coins the term and is known as the father of geography. And so that you are fully understanding that there's a thing of flat Earth going on, because I guess it's funny, but it's also really stupid. And so this dude more than 2,200 years ago accurately measured the circumference of this globe within 100 miles. We couldn't check that and verify it until about 1960, I think, is when they knew the full true circumference of the Earth. So that the old Greeks, as Eratosthenes and Plato and Anaximander and Socrates and all the rest, these dudes were really learned, and they understood the world really well. But we now know more with more technology. So Earth is in fact an oblate spheroid. That means it's wider around the middle and shorter. The distance to go around the equator is longer than to go from pole to pole all the way around the Earth. So we know this because of centrifugal force, and that's that. Mount Everest is the highest peak on the Earth, but depending on what you want to call the highest mountain, depends on where you're measuring from. So mean sea level means Mount Everest is 29,030 feet high and growing by a few centimeters every year, which would fit very easily in the deepest part of the Earth, the Mariana Trench, as you see. I think Chimborazo down in South America, I think that's the one that's, if you measure from the center of the Earth to the peak itself, that's the tallest mountain. If you measure from the bottom of the ocean to the peak of the mountain, I think that's Mauna Loa or Mauna Kea, one of those in the Hawaiian Islands. But anyway, it's just a matter of how you're measuring. But the life layer that we're really going to be talking about is the lower portion of the atmosphere, the area which we inhabit on the surface of the Earth, and only a little ways down into the Earth itself. Everything else, not so much. That said, though, I want to challenge the way you see the Earth. So where it says, what's wrong with this picture? There's absolutely nothing wrong with it. In space, there's no such thing as up and down. So we do have an ecliptic plane, which we kind of see most of the planets lined up on. Mercury's a little off. If you were to look at Pluto, no wonder they demoted it to a dwarf planet, because it was so odd in its passage around the sun, taking nearly 1,000 years, and at times it was closer to the sun than Uranus was, Neptune, the outermost of the Jovian giants. Anyway, space is really different from the way we tend to think about things, and so there's no up and down in space, and gravity holds us all here, and so forth and so on. Looking at globes, nobody really carries around globes anymore, but they're the most accurate representations of planet Earth, to be honest, because they're round. When we flatten things out, we introduce errors to the map. If you look at things like great circle routes, those are the shortest distance between 2 points over a long area of the surface of the Earth. So if you get on Google Earth, and I'll show you this maybe in a later video, but to stretch a line from one place to the next means you're going not as you typically would see it represented on a map. So the map flattened out is distorted. So we use things like great and small circle route to show you the shortest distance between 2 points. So for instance, flying from Chicago to Tokyo, we'll fly up through Canada and across the middle part of Alaska before heading south again. You go northwest and southwest to get to the place. And so this is easier to represent if you were actually playing with it within Google Earth itself. But just trying to show you these things. And looking at the circle of illumination, this is one of the most popular pictures ever made. It's from the surface of the moon. There are many pictures of this. The very first one is the most popular, but all I'm really trying to represent here is Earthrise, but also the circle of illumination. So that the sun can only illuminate half of the globe. So some of us are in daytime and some of us are at night at all points of the clock. Okay, I'll come back to that clock issue here in just a second. The coordinate system we're going to use here is latitude and longitude, but there's other ways of looking at it too, like with a grid cell. So whereas Cleveland, Ohio, but at F3 where they intersect. There's lots of different kind of mapping and metric, but I'm going to stick mostly with the coordinate system you're used to. Okay, so looking at that, looking at latitude. Equator is the baseline. You have this in the lab too, but I said I thought I needed to cover some of this. If you've watched this in the lab, still hang with me for a moment. So this is measuring distances north and south of the equator. Now here's the deal. To speak intelligently and accurately about this, don't tell me that the lines run east to west. That's not really what's happening here. These are parallels, meaning they'll never intersect, and they go from 0 up to 90, which is a point, or at the North Pole, or south to the South Pole, which is a point. The rest of these are measuring distances north and south of the equator. So 34 degrees north longitude is where you'll find LA. And why? Because at the center of the Earth, if we draw this out, and we can see the arcs here. Again, Eratosthenes did this quite eloquently when looking at the world. He looked at, the Greek sweet spot, but then he looked at the torrid parts of desert in Africa and the barbarian wastes of northern Europe. And so he found that sweet spot where smart people were. Obviously, it's where he lived. But the way we break this down further on seeing more and more minute pieces of the planet, then we've got to add to that minutes and seconds. So we break these things down just like we would on a clock. So longitude is the same thing, but the baseline being the equator, and then as we get closer, looking at maybe trying to find a place like Gallatin on the map, we would add minutes and seconds to that. Okay, now that's for latitude. For longitude, we're measuring from a degree of line here that runs through Greenwich, England, which is the baseline of longitude. Okay, so if you've never been to the museum and everything there, all the clocks and astronomical charts and telescopes and everything else, it's really very cool. I had to make my pilgrimage. Any good geographer should. But going to London will basically get you there. And the counting is the same, except for instead of where latitude goes up to 90 degrees, longitude goes up to 180 degrees. So it goes diametric opposite where Greenwich is in England to the back side of the Earth, which you can't see unless we flatten it out. And those are your counting methods, okay? Making an eastern hemisphere going this direction from Greenwich and a western hemisphere going this direction where the United States and South America is, okay? So if we throw it all together, we can see that Los Angeles is at 34 degrees north latitude and what's this one? 180 degrees west longitude right there, okay? So that's how we find a place using degrees. Okay, so pretty straightforward, but I'm going to introduce here to you that there are some mappings that use quadrants, plus, plus, minus, minus, plus, and minus, minus, and so this is typically done when you're involving computers, because computers don't like minutes and seconds like I was showing you over here, degrees and minutes and seconds. They don't work that way. So it's basically a full degree marking and then some portion of a number 1 behind it. So I think I've got it set up here to show you this. This I don't need to go over. I kind of did this. Well, do remember parallels and meridians. Meridians of longitude measure distances east and west, and parallels of latitude measure distances north and south. So I'm going to skip over this. There's what I wanted right there. So I wanted to show you what happens inside of a degree. Okay, so to look at it here, the way they have it set up is this is 5 degrees, 59 minutes, and 0 seconds north. And so they have a full minute laid out here because the next minute, when it ends, takes you to a full 6 degrees even. Okay, 6 degrees north latitude. Okay, so in looking at the split between those, okay, so it only goes to 60 because that's what minutes go to, not 100, 60. So halfway between 59 minutes and the new degree is going to be 59 minutes and 30 seconds. So at 5 degrees, 59 minutes, and 30 seconds is that line right there where you see C. Okay. If you're going for longitude, here's going to be what we're counting from, 71 degrees west longitude to 71 degrees in 1 minute. So as we go from this one to the west, we're going to go farther west here. And if we go half, a quarter, a half, and then 3/4 of the way, we're going to say what? Well, it's 45 seconds within that time frame of going from 0 to 1. So again, the distance is the full minute. The seconds within it then are 45 or 30 or 25. And when you finally get to 60, you roll it back over to zeros and then add the next minute to that. And I hope that's clear. So understanding, you would have to have a larger and larger scale maps to go in really close and see the use of minutes and seconds. But that said, we also see in, pardon me, in computers that, again, they don't like degrees, minutes, and seconds. So if you look at something like 48 degrees, 28 minutes, well, 28 with 32 seconds on there, that's pretty close to half, right? Almost 30. So when you look at it over here, you'd see 48 degrees, 0.4756. Okay, the degrees thrown on there. So that's almost halfway, up to 50. And so the way the decimals work and the decimal degrees with the computer, same way. They just make sure, like this one is close to 20, so that should then be a third of the way. If 20 is a third of a minute, 20 minutes is a third of, a degree, then that'd be like, 20 here, so that'd be 33.333 if you got it at exactly 20. So I hope those things make sense to you. I hope they're clear. Now, I'd like to talk about longitude for just a moment and see how the time zones work. These came as a time zone conference that was held in the United States in 1884 to determine where the time zones would be. And there's 24 hours in a clock, 360 degrees in the Earth as a circle. And so 24 goes into 360, if you'll do the math real quick, a beautiful 15 times. Okay, so what they then said is, hey, 15 degrees is every hour represented across the globe. So here is the Greenwich meridian, okay, the baseline of longitude, and 7.5 degrees east and 7.5 degrees west makes 15 degrees for a time zone. Okay, so looking across the top part of this image here shows you 24 different time zones, and if we get right here, the international date line where all new days begin. Okay, so on this, pardon me, if the time there is, say, 10 o'clock in the morning, well, it's 10 o'clock on both sides of the line, but it's 10 o'clock of the new day on the east side, or the west side in the eastern hemisphere, and 10 o'clock in the old day. So this is going to be, say today is Monday. So here it's Monday, but it's already Tuesday in places around the world. No, all you'd have to do is count that to see it. So where I am, it's 4:30, and that's the Central Standard Time Zone. So it's 4:30 p.m. So 5:30, 6:30, 7:30, 8:30, 9:30, 10:30, 11:30, 12:30. So from this line right here, all the way over to the international date line, it's already tomorrow. It's already Tuesday. Okay, so understanding how the clock and it fits the map works is a really big component here. So I wanted to make sure you were comfortable with that. I'll come back with a little bit more since I'm about out of time. So check back with me on the next lecture. See you in a minute.